All right, let's dive right into this explainer. We are going to transform a highly technical application note into a truly actionable playbook for diagnosing real-time performance issues using BTFViewer. Look, if you've ever stared blankly at a misbehaving embedded system, wondering where on earth your CPU cycles just vanished to, well, grab your magnifying glass. You are in exactly the right place. Because, let's be real, debugging embedded systems can feel like a total nightmare. The bugs are transient, they're timing dependent, and honestly, they're practically invisible. But framing BTFViewer as your ultimate detective's magnifying glass provides a pretty heroic solution to these mysteries. It takes all that abstract scheduler behavior and turns it into concrete visual evidence. To tackle this, we're organizing our investigation into 5 main suspect categories today. 1. Meet your RTO detective. 2. Interrogating CPU load balancing. 3. Uncovering hidden timing delays. 4. Solving complex concurrency crimes. And finally, verifying overall system health. So let's start with Section 1, Meet Your RTOS Detective, Getting Oriented in BTViewer. Loading your trace is literally as simple as running a quick Python command in your terminal. Boom, you're in. Instantly, the status bar gives you this nice high-level view of task counts, segment counts, and the total trace span. But here's your first big choice: task view versus core view. Now, if you're on a symmetric multi-processing or SMP multi-core system, core view is absolutely going to be your best friend for a first glance. You can instantly spot which cores are busy and which are just idling without getting bogged down in individual tasks right away. You just click a core label and it expands its per-task subrows. Moving on to Section 2, Interrogating CPU load balancing, Finding the processing power hogs. Our first major investigation here is tracking down exactly how much CPU time each core is chewing up. Say you spot a massive imbalance, like one core is completely pegged at 90% while the others are practically taking a nap. Well, you likely have a poor affinity configuration, or maybe tasks are just improperly pinned to a single core. In that case, you'd want to jump over to the core affinity table right away to verify what's actually executing against your declared affinity masks. So the magic number to keep in mind here is 100. A load balance score of 100 represents perfect balance, which is actually based on the Gini coefficient. A score of 0, well, that means one core is doing absolutely everything. But BTViewer is pretty smart about this. The badge will actually flip to amber if the standard deviation jumps over 30%, instantly signaling that you've got a significant workload imbalance that desperately needs your attention. By really interrogating this core utilization data, you can start matching symptoms directly to causes. For example, if all your cores are running super hot except for one that's consistently low, you might be looking at a serialized bottleneck, like a lock or a queue. The immediate next step? Go check the mutex or preemption chain tables. Or, hey, if the idle percentage is unexpectedly high everywhere across the board, maybe tickless idle is kicking in. You can easily verify that over in the Trace Health section. All right, Section 3, Uncovering hidden timing delays, tracking down worst-case execution time. To actually find where the lag is coming from, we have to separate our metrics. Execution time is strictly the time spent actively on the CPU. Blocking time, on the other hand, which is sometimes called response time, is that off-CPU gap from the moment one slice ends to when the next one begins. Add those two together and boom, you've got your total inter-arrival time. Now, to find your worst-case execution time, or WCET, you just follow a few quick steps in the UI. Open up statistics, navigate to execution time per slice, and just sort that max column descending. And here is the absolute best part. That max cell is actually a clickable link. You click it, and the viewer snaps your timeline exactly to that longest task slice, zooms right in, and drops a bookmark annotation there, so you can immediately investigate its context. It's brilliant. When you click a task row, it opens up a distribution chart. And a quick tip here, if the max slice shows up as a massive isolated spike in the scatter plot, like way above your 95th percentile line, you should really suspect external interrupts or OS overhead rather than a regular execution delay. The blue CDF curve on the histogram will quickly confirm if this is just a rare tail event. Because if your 95th percentile is already sitting near your deadline budget, yeah, that's the number you really need to worry about for your design margins. Which brings us to Section 4, Solving complex concurrency crimes, catching priority inversion and core bouncing. This is where we tackled the most notorious RTOS bugs out there. Think of classic priority inversion geometry as a literal crime scene. You've got medium tasks, RM suspects, stealing time, while a critical high-priority task, H, is stuck waiting on a resource that's being hogged by a low-priority task, L. So in any priority inversion episode, you're looking at these three primary suspects. And BTFViewer makes catching them incredibly easy if your trace includes priority events. Look at the timeline. You can actually spot the low holder just by looking for a red bottom stripe on the task subrow. That red stripe, it marks the exact priority boost window from the moment the kernel triggers a priority_inherit event right up to the priority_disinherit event, which is what prevents those medium tasks from preempting it while it holds the mutex.
But beyond just inversion, we really need to interrogate core migrations to hunt down lock-induced core bouncing. This nasty little bug happens when a task grabs a mutex on one core and then releases it on another. It drives up unnecessary overhead and triggers a core migration while held warning, which, yeah, is exactly as bad as it sounds. To track this, you can check the ping pong count for immediate reverse migrations, or even better, open up the migration heat map. It visually clusters migrations into time bins. Click a hot cell in level 1 and you drill right down into level 2 per task sub-bins to see exactly when and where the bouncing is happening.
Finally, Section 5, verifying overall system health, deadlines, budgets, and tick jitter. To verify the system's overall health, we need to ensure deadlines are actually being met. You can set a global CPU budget percentage in the settings, let's say 25%. Once you configure that, BTFViewer automatically plays the enforcer, flagging any task whose active CPU time creeps over that 25% threshold and putting it in a dedicated CPU budget exceeded table. By setting strict task deadlines in nanoseconds, any slice that goes over budget gets immediately flagged. But you also want to keep a close eye on the trace health section for the scheduler tick. You can quickly spot if long critical sections are causing missed ticks, which is usually the case when your max tick period is significantly higher than the average. Or if you're seeing a high coefficient of variation in your tick intervals, you're definitely dealing with severe tick jitter, likely caused by interrupt latency. It'll even throw a tickless badge if it detects an intentional low-power tickless mode based on large gaps. And there's this step-by-step filtering procedure that is just incredibly powerful. You simply left-click the timeline to drop cursor 1 and click again to drop cursor 2 right around a specific region of interest, say a massive, suspicious load spike. Once you enable Limit to Cursor Range in the Statistics panel, all your metrics, your tables, your charts, they instantly recalculate for that exact window. Scoping your analysis like this completely cuts out all the statistical noise from the rest of the trace. And once you've solved the mystery, well, you don't even have to open the UI the next time. You can export all your findings directly to an HTML or CSV report using the headless command line interface. Imagine automating BTFViewer P report right into your continuous integration pipeline. It basically acts as a permanent, automated guard dog for your system's timing constraints, ensuring performance regressions never make it to production again. Armed with this investigative playbook, from catching priority inversions red-handed to pinpointing your worst-case execution times, you are fully equipped to load up your own trace files and uncover exactly what's bottlenecking your system. The invisible bugs, they are finally visible. So, the only question left is, which RTOS bottleneck are you going to hunt down first?